Hey everyone, and welcome to this our next video, bringing you further insight into the OEMx tool brought to you by exida. And today we are looking at a new advanced feature that's built into the tool, and this is our custom environmental profile editor. Just to give some context, if we go to project drop-down menu, project environmental profiles, as you can see here is a list of all the default environmental profiles that are built into the OEMx suite of tools. We go to the help menu, give further context, we go to manual, it brings up the OEMx manual, and if we go to page 49, this shows us all the default environmental profiles built into the tool and all the different metrics associated with them and the particular settings for all those individual profiles. So keeping that in mind, minimize that, and we'll go back to our project drop-down menu, custom environmental profile, and this brings up a new editor window. And this allows us now to basically create our own environmental profile. Now, the difference with this particular editor window, unlike other editor windows in OEMx where you can put in your numerics or information and then just X out of it, but they're saved, similar to the edit project details window. This one, you actually have to save it as a separate external file that OEMx then reads. So if we go to File, you can see we have the options of a new profile, Save As, or Open an existing environmental profile. Now I'll show you the open an existing profile and where that might be beneficial when we're finished. But we're going to start from scratch here. We're going to call this Robotics. Call this Robotics 1. So we're just giving it a name. This is no relevance or reference to the actual file save name. This is just a name for the environmental profile that will be listed in the drop-down menu in the OEMx tool. So the first option we have is mechanical dynamic. This particular option is only applicable to mechanical components in the CRD. So by checking this, it will have no impact on our electronic components. For this particular environmental profile that we're creating, because it's for electrical electronic components, we're going to leave this particular box unchecked. The next option we have is board coating. So for this particular profile, environmental profile, we're basically building up a picture of the environment that we want to do our analysis in. Does our PCB board have a particular coating, maybe some type of resin over the board, an added layer of protection? We're going to actually say yes for this one, so we check this box. The next option we have then is humidity, saturation, condensing. So this is a binary option again. It's either on or off, non-condensing, which is unchecked, or condensing, which is checked. We're going to leave this non-condensing, so we leave it unchecked. Next option we have is the average ambient temperature. For this, we're going to set a figure of 60 degrees Celsius. And just to keep a note that obviously there's normally a relationship between the average ambient temperature and the average internal product temperature. Obviously there needs to be a delta between the two to allow cooling to happen. So just to keep in mind, we will have to change the average internal product temperature when we get down to that option. I want this to be a particularly warm environment just to make it particularly harsh environment, so I want to set this at 60 degrees. The next thing we look at is our humidity. I'm going to set in a value of 20, and now for high humidity I want to set a value of 80. Just before I continue entering that in, as you can see here, I put in a value of 8. Box is turned red, which is obviously an indicator that there's an issue or an error with the value I put in. We hover over it, you can see it's telling me must be within the range 40 to 100. That's grand. Put in the 0, gives us a high humidity of 80. Happy with that. Move on. Next number, or the next value we're looking at, is the average altitude in meters. And this is in reference to our relative flux density number, numeric. 0 is obviously at sea level. It gives us a relative flux density of 1.02. Just to show you some context, I'll put in a value of 1 kilometer, gives us a relative flux density of 2.36. And what the implications of this value is, for any semiconductor based components in our design, with small gate geometry that would be susceptible to gamma ray radiation, causing bit flips, whether it's single, double, or multiple bit flips. This value will obviously increase the fits for those particular components. So that's what the RFD is in reference to. Part of the calculations, I'm going to drop this down to 100 meters above sea level, and as you can see, our relative density dropped to 1.11. Next thing we're going to look at is our electrical overstress. This gives us an option of low, medium, and high. Is our particular product that we're doing the analysis on exposed to transients or some other type of electrical stress? I want to say high. Yes, it is. It's a particularly harsh environment, so we'll set that. Next thing we're going to set is the salt chemical corrosion. So the environment that this product is in, the air quite salty or some other type of chemical that can cause corrosion, possibly something like a mine maybe. So again, I'm going to set this value to high. And lastly then we have mechanical shock vibration. So is this in an environment where there is a lot of mechanical vibrations, the product's been shook about, a lot of movement in that regard? So again, yes, it's some type of machinery causing a lot of vibration movement. We'll set that to high. Now coming to the average internal product temperature. As I said, this will have some relationship to the average ambient temperature. This is over the course of a year. Just, all these figures are over the course of a year. So the average internal product temperature, I'm going to increase that to 75 degrees. I'm going to say that that's for 80% of the time, 80% of the year. Now what I want to do is add an extra stress entry. And I want to say that for 20% of the year, the temperature can rise to 100 degrees. So that's our average internal product temperature. And then lastly, next thing we need to look at, or the last thing we need to enter in, is the temperature cycle, if one is applicable. And this is basically down to how often is the device powered off and back on again, power cycle. And this again is over the course of a year. So if we look at this first example, the figures that are in for default has a delta temperature of 5 degrees and 365 cycles. So that means that once a day, this product is powered off and back on again. For this second example, this means that once a year, this product is cycled off and on again. I'm going to add in a new one where I want a delta of 20 degrees. I'm going to enable this particular option, and again, I want 365 days. So once a year, once a day, this product is cycled off and back on again. This is our new environmental profile. Now all we have to do is go to File, Save As. We give it a name. We call this robotics. So we've now saved our robotics 1 environmental profile. So we can now exit out of that. If you go to Project, look at our drop-down menu. Have robotics 1. This one is one that I created previously and deleted, but this is our new one. So we select that. So that's our robotics 1. And just to close the circle, if I go to Project, Custom Environmental Profile, and I go to File and Open, we can now open our robotics 1. As you can see, it's opened up the environmental profile that we've just created. We can now edit this, save it as a new second environmental profile using the existing one as a baseline. So that's the new feature built into the OEMx suite of tools, our custom environmental profile.